welcome everybody to another TWed of the fall 2020 season. A little bit of logistics. As with all of our TWeds, we are recording them. We will make them available through the Tetherless World TWed YouTube site, and also possibly, depending upon general interest, in the IDEA website, where there's podcasts and videos and lectures list catalog. Without further ado, we're welcoming, I think he's a tenured grad student, Sabbir, and he's going to give us the talk about semantic data dictionaries. So Sabbir, just a quick logistical question. Are you open to people interrupting and questioning, or would you like to go through it and take questions at the end?
So maybe people can comment in the chat and then you can interrupt me and then call on people.
I'll interrupt you if there's something urgent. I'm not going to interrupt you just if people are throwing questions. But if I feel like, and I always take prerogative to interrupt if there's something I think that needs to be highlighted. But generally, we'll just let you go. Okay.
Mm-hmm. So, but I'm open to interruptions. That's fine.
All right. So take it away, Sabbir. Thank you.
Sure. This talk is called Annotating and Transforming Data with Semantic Data Dictionaries. It's based on a recent journal paper that was accepted to the Data Intelligence Journal, which is linked in a later slide. And the co-authors on that paper are from a variety of different groups, and other institutions have worked on this project as well with us, who aren't listed here. But the co-authors on the paper are a combination of researchers from Tetherless World, IBM, UMFG, University Federales Minas Gerais in Brazil, and Columbia University Mailman School of Health. So it's been a highly collaborative approach to get to the point we are now with semantic data dictionaries. So there's 6 main sections for this talk. So I'll begin by introducing this work, which includes motivating its importance and presenting some of our claims. Then I'll go through some of the related work. I won't spend too much time here, but I'll touch upon literature related to traditional data dictionaries, data integration tools, mapping language approaches, and semantic ETL. And then finally in section 3, we'll discuss the semantic data dictionary and the various components included in the semantic data dictionary. Then in part 4 of this talk, we'll go through some examples. And then I'll briefly discuss some of the evaluation we did, but I'll point the readers to the paper to take a closer look at the evaluation. And then we'll conclude with some closing remarks. So we'll begin by introducing the work, motivating its importance, and presenting our claims. So just to quote the definition of a data dictionary from IBM, a data dictionary is a centralized repository of information about data, such as meaning, relationships to other data, origin, usage, and format. So the concepts highlighted here in red are very important to think about, especially when we're thinking of how do we actually assign a semantic meaning or a semantic representation to data. What are some things we want to include? Are these already included in traditional data dictionaries? Even so, what are shortcomings these traditional data dictionaries might have? So with that in mind, some limitations of semantic data dictionaries are related to ambiguity, standard adherence, and human consumption. So while the use of data dictionaries makes understanding the meaning of data more readily doable than without having the data dictionaries, what is meant by the contents of a data dictionary might be ambiguous, in the sense that 2 people looking at the same data dictionary might come up with different interpretations as to what the text description might mean about the data column. Part of the reason why this happens is because traditional data dictionaries don't adhere to a common standard. So within institutions that might use data dictionaries or medical facilities or companies, there might be a standard within that institution, but the standard usually isn't shared across institutions. So if you look at a data dictionary from one group, it might look completely different from a data dictionary made by another group. So these data dictionaries themselves are made for human consumption. So they're meant for humans to read to then have a better understanding of data that they might have downloaded and decide to use. However, in general, these data dictionaries are not meant for machines to consume. I'm sure they might be in tabular files, which you can then load into a database or something and parse the text, but the text itself isn't necessarily readily ingestible by a machine. So to address some of these limitations, we believe that semantic technologies can help. So the use of existing semantic technologies and standards will help reduce ambiguity as well as standard adherence. And because semantic technologies are designed for machine consumption, by having a semantic model for data dictionaries, machines as well as humans can take advantage of the information in these documents. Another limitation of traditional data dictionaries are that usually when you have a data set, it's describing some object, but what's recorded are the attributes associated with that object, rather than information about the object itself. So for example, if you have like a demographic data set about a person, you might get attributes such as their hair color, their race, their education level, stuff like that. But usually these data dictionaries don't include annotations about the person themselves. So this is we refer to as implicit concepts that are implicit within the data itself. And in the database world, this is called object elicitation. And finally, while some provenance is included in traditional data dictionaries, we believe that more information as to how the data might have been generated or how it was derived or where the definition came from, stuff like that, more provenance information can help users better understand these documents. So as well as addressing some of these limitations that I mentioned before, I list 3 motivating factors for this work. So people who use data may want to annotate data from various domains, and they don't want to use different tools for each of these different domains in general, especially for multidisciplinary research. So we desire an approach that is domain independent, that can be used across domains. So like data integration, which is one of the related works we'll go through, one of the goals of this work is to harmonize data from multiple sources. So how can we integrate data such that concepts that refer to the same resources are linked kind of automatically, and concepts describing the same things are using the same unique resources, such as classes from ontologies. And finally, we want to have a better understanding of the data. So what does that mean? Well, we want us as humans to understand what the original data provider was recording when they were recording the data, as well as we want this information to be understandable by machines who may then process the data. So you can imagine that as data gets processed down the line, some of this inherent information is lost. So if the data providers themselves were the ones recording this information, then this information might be preserved down the chain of use. Okay, so we make several claims, 3 of which are listed here. So the Semantic Data Dictionary is an approach for annotating and transforming data, as the title of this talk implies. As I've just discussed, one of the claims we're making is that we're addressing some of these limitations of traditional data dictionaries. So that was like limited provenance, human understanding, ambiguity, those kind of things. Another related area I'll be talking about is mapping language-based approaches. So this is kind of the more traditional approach for semantic web researchers to transform data into these knowledge graphs or knowledge graph fragments, ontologies, whatever. However, while this practice is somewhat standard across semantic web computer science researchers, a domain scientist who's not trained in computer science may have a very hard time using these mapping language-based approaches, which in addition to learning some programming framework, they also have to learn this new language, which they often don't want to do. So we claim that our approach provides a layer of abstraction over these mapping language approaches where these domain scientists then don't have to learn this new language. Finally, we claim that the artifacts generated by our approach are fair, so findable, accessible, interoperable, and reusable. And these metrics are part of our evaluation, which I'll discuss later. So hopefully you'll be convinced by the end of the presentation that this content is fair. Okay, so that was introduction to semantic data dictionaries, and more so we're introducing traditional data dictionaries from which we want to get a more semantic representation. So what are the related work related to this? Well, as I mentioned, there's traditional data dictionaries and data integration and mapping languages, as well as semantic ETL, which I'll discuss a little bit further. So traditional data dictionaries, there are several that I've come across when doing some of the research for the journal paper we wrote, but some of the more clean ones are data dictionaries used in patents, which we probably can't use because they're patented. But then you have stuff like the Stony Brook Data Governance Console, the Open Science Framework, which is what you're seeing here. This image is from the Open Science Framework. So this is what a data dictionary might look like from that, and the project Open Metadata Schema. So actually, before I continue, I'll just click one of these links. I'm assuming you can see this. So this is the Stony Brook University Data Dictionary Standard. So stuff like table name, data elements, definitions, the data source, date created, date uploaded, some notes. It has a few things. Then we have the Open Science Framework, which was what we were seeing this image over here. This has a little bit more things, so measurement units, allowed values. We see the definition again. This includes synonyms, and as well as links to other resources the data might be related to. And then something like Project Open Data Metadata was actually one of the few data dictionaries I came across that actually uses semantic web standards. So of the traditional data dictionaries, I'd say this one was pretty good. And it has different types of tables associated with it. So you have like catalog fields, which might be related to dataset metadata, even more dataset metadata stuff like the title, description, publisher. And then you have dataset description stuff like is described by, and this is based off DCAT. So it's actually using a vocabulary from the W3C. It's using an ontology as part of its framework. So of these traditional data dictionaries, if I were to recommend one to use, it'd be the Project Open Data Metadata Schema. So these traditional data dictionaries, however, have several limitations. First and foremost, there's a minimal incorporation of semantics. So other than Project Open Data, the other data dictionaries we explored didn't even use semantics at all, or they weren't linked to classes and ontologies. As I mentioned before, this idea of implicit concepts within the data, most of these approaches don't allow for object elicitation, which we want to do to have a better description of what the data is actually talking about. Most of these approaches were domain specific. So for example, this biosystematic database of world Dipteria was just kind of like a biological taxonomy type, and it had very domain specific concepts within the data dictionary. Almost all of these data dictionaries, except maybe the Project Open Data one, are not machine readable. In the sense where the machine won't be able to understand exactly what you mean without doing some post-processing. And there's no formal standard across these sets of data dictionaries. So if you look through these data dictionaries, they all have different, maybe sometimes overlapping, but different components that they're including. So this is related to the field of data integration, because what we're trying to do is create a unified view of data from multiple sources. So common data integration techniques, or some popular ones that we looked at, was SWIT, which is a semantic web integration tool, RDFgen, DataOps, and OpenRefine. However, there are some limitations associated with these tools. So not all of these tools are open source. Some tools, I don't think it's listed here, but Karma is also another popular data integration tool, which uses a mapping language, KRML. So some of these data integration tools have the same difficulties that mapping language-based approaches have, in that you have to learn a mapping language in order to use them. In order to get a subset of the data you want to annotate or do cell-based operations or merge different data sets, these kind of tasks are very difficult in general with these tools. Kind of similar to the problem with traditional data dictionaries, these approaches in general don't allow for object elicitation. And then finally, someone from a domain outside of computer science, like an epidemiologist or someone, would probably be reluctant to adopt some of these tools due to the learning curve associated with it. So I'll just talk briefly about some mapping languages here, which is kind of the traditional semantic web way about going about turning data into knowledge graphs. So R2RML is probably the most popular mapping language, as well as RML, and there's other languages derived off RML or R2RML, like XR2RML or KR2RML. Oh, so I mentioned Karma here. So Karma is both a data integration tool and a mapping language. Well, actually, KR2RML is the mapping language for Karma. But I guess I included here because it requires a mapping language to use. There's also SML, which is a Sparkle-based mapping language. Actually, a lot of these use kind of some constructs from Sparkle, but SML is kind of the most Sparkle-based one, and RDB2OWL. So RDB2OWL is pretty interesting because while all these other mapping languages create knowledge graphs, so instance data, RDB2OWL actually creates ontologies, which is interesting. And the diagram you see on the right is the R2RML kind of approach. So they have a triple map, which links to a predicate map and an object map and a reference map. And there's also a subject map and a graph map. And all these maps are written in RDF but there's some RML specific syntax. So pretty much the main challenge with mapping languages is that you have to learn a mapping language to use them, right? So domain scientists may be reluctant to do that. And then finally, we have semantic extract, transform, and load, which is semantic ETL. So ETL refers to processes that read data from a source, convert the data into another format, and write data into a database, which is kind of what we're doing. So we're reading data from a tabular structure. We're converting it into a RDF-based format, which then you can load into a triple store or something. So one of the most popular linked ETL approaches is the linked pipe ETL, which is the diagram shown here. And the reason this is popular is because it has kind of this graphical user interface where you can define input configurations and conversion processes and all this stuff. But even if you go through the tutorial, to actually do this yourself for the file you want to convert, it might be quite complicated. So there's a little bit of a learning curve associated with it. Semantic extract, transform, and loader is another subtle approach, settler, which was actually developed by this lab. And what's kind of nice about this approach is that it allows you to convert data that isn't just tabular in nature. You can convert data from web pages by doing web scraping techniques. You can convert data from XML-based structures, stuff like that. But again, you have the challenge. You have to actually write the mapping script. And so there's some, I want to say coding associated with it. But it's not exactly coding, but there's some language writing. Eureka is another approach, and LDIF is another semantic ETL approach. Eureka seemed pretty good, but I don't think it's freely available anymore. And LDIF also had a pretty hard learning curve, but it is one of the more popular ones, though it is about 10 years old now. All right, so that's it for the related work. I guess before I continue, in the paper, we also discuss several standards in terms of related work. So the reason we're doing this is maybe sometime along the line, the Semantic Data Dictionary specification will be its own W3 standard, but we're not at that point yet. But so certain standards that we looked at are like the CDES standard, the IOC 1799 or something. I actually don't remember them off the top of my head, but there's also the FAIR principles that we looked at, which aren't necessarily a standard, but they're kind of guidelines for how you should publish your data. So pretty much what I'm getting at is we looked at existing standards when we were coming across how we should formulate our approach. Okay. So the Semantic Data Dictionary specification pretty much is a collection of 6 other specifications. So first of all, you have the INFOSHEET, which links to the other Semantic Data Dictionary tables or specifications. And also, we have included the metadata supplement to the INFOSHEET. So if you want to add metadata about your data set or about the resulting knowledge graph, you can do this in the info sheet. And we'll go through an example a little later. There's also the dictionary mapping specification, which is kind of like the bread and butter of this approach, where you can get rid of everything else. As long as you have a dictionary mapping, you can turn a data set into a knowledge graph. So the dictionary mapping is pretty much where you're mapping the explicit columns in the data set, as well as these implicit objects that you may also want to annotate. So then you also have the codebook, which is used to annotate coded values. So for example, say you have a demographic data set and there's different races in in that data set, and maybe like different ethnicities, whatever. Asian is denoted with code 0, white is denoted with code 1, African American is denoted with code 2, European is denoted with code 3, whatever, right? So within the data set itself, the values are codes. Well, we can use a code book to assign those coded values classes from ontologies so that when we're doing the conversion into a knowledge graph, those values themselves also get annotated. So pretty much this is value annotation on top of the column annotation, which this itself is one thing that a lot of earlier data dictionary approaches were missing. So it's a pretty interesting contribution of this work. So there's also a code mapping, I guess, table. So I'll actually pull up an example. So this is the code mapping table used in the chair project. So pretty much when you're doing annotations, you're assigning class values to concepts in the dictionary mapping or whatever. But some of the class URIs from ontologies might be hard to remember. But maybe they have a shorthand notation, like this oboe UO 11 concept refers to an ampere, but you can remember just put amp or put A for ampere or 1 over S for a cycle or whatever, right? So CM is, where's centimeter somewhere? Centimeter squared, centimeter cubed. These URIs might be hard to remember, but notation like CM will be pretty easy to remember. So as long as you import a codebook, you can just use the shorthand notation directly in the dictionary mapping or codebook tables. So as long as you include a code mapping table like this. So that's what the code mapping is for. Go back to full screen mode. So the dictionary mapping itself does include a column for time. So if you want to associate a concept with having some time, you can do that directly in the dictionary mapping, but sometimes you need more complex temporal mappings, and that's what the timeline is for. And then finally, okay, so one thing I mentioned before is that you want an approach that you can reuse regardless of your domain, right? So approaches that do that are called domain agnostic. But in the semantic web world, there's this idea of an approach also being ontology agnostic, whereas it does not depend on a specific or a set of ontologies, right? So in order for our approach to be ontology agnostic, we have included the properties specification. So there's our model is based on the semantic science integrated ontology, SIO, and we use a lot of concepts from SIO and Prov as kind of a default. But there's people who don't like SIO, or they want to use BFO or another general level ontology because that's how other things in their application are being rooted. So the properties specification allows you to change the inherent RDF predicates that are being used, so you can change it to another ontology of your choice. All right, so so this is what the INFOSHEET specification and metadata supplement looks like. So the INFOSHEET simply links to the other tables in the Semantic Data Dictionary, and the metadata supplement allows you to include additional annotations about that data set or the STD. So there's been a lot of discussions amongst the authors as to what to include in the supplement, and this is kind of like the short list of things that we decided to include. And these were based off data on the web best practices and HCLS, the Semantic Web Healthcare and Life Science Working Group, which are linked here. I can share the slides after, and then you guys can explore these links. I won't go through it now. But pretty much the info sheet allows you to include both links to the other tables as well as metadata about the dataset. So this you can kind of think of as kind of like the configuration document of the STD specification. Next, you have the dictionary mapping, which is kind of like the bread and butter of the whole approach. So pretty much, what do you need to describe a column in a dataset? Well, first of all, you should tag that column with a class and an ontology. So the column itself might be an attribute such as hair color or height or weight or something like that. Or it might be an entity such as like the location or organization or something else. So something that's not an attribute. The column itself could be describing an object. So the mapping of this both uses RDF type. So from a representational perspective, it doesn't really matter if you put something as an attribute or an entity, but certain applications that use semantic data dictionaries might want to distinguish between those. So we included both these columns. And then you can include, if you assign the column to be an attribute, you can say that it's an attribute of something. And I'll go through some examples to make this clear. You can add a time component. You can add a format. You can specify a unit. There's this idea of a relation. So you can actually, if one of these properties included in the specification is not what you need to use a different property. Well, you can use the relation column in the Semantic Data Dictionary to customize what property you're using. So you can fill out relation with a custom property, like example has first name or whatever. And then in the relation to, you would put what that property is pointing to. And I think we see an example of this later. If you have something like an entity, like a student or whatever, they might have a role like a student role, or if you have like a subject in a study, they might have a role like a subject role. So you can include that in your annotation. And also the two main forms of provenance we recommend including are if you have this information, the derivation information and generation information. So how does this actually get mapped into a semantic form? Well, the formalism for mapping is pretty straightforward. Most of these are kind of like one-to-one mapping, where if you have a column and you have an attribute or an entity, it assigns the attribute as a type of the resource that gets created. If you have a column and a label, it gives the column a label. Same with comment, definition. If you have an attribute of, it uses a SIO attribute of property. If you add a unit, it assigns the unit to be a unit, and then it uses the has unit to link the instance of that unit to the column. All the cell values get, so if you see in the bottom column and value, so if you have a value in a cell, it uses SIO has value. But if you have a value, a cell, and the format, it tags that value with a specific format. If you have the time, the default property is SIO exists at. So the only thing that's really complicated, which isn't one-to-one mapping, is the use of role and relations. So part of this is because this whole custom property use of relations, and also this is kind of multiple loading on these concepts. So if you include both a role and a relation, it assigns a role in relation to the relation. But if you just include the in relation to, it just assigns in relation to. But if you include a relation and a in relation to, the property it uses is what you provided in the relation. That's kind of the customization I was talking about before. If you have all of these things, it includes all of these. So you can have a role and a custom relationship mapping. Okay, so the next table is the codebook table. So the codebook table is a lot simpler. All the mappings are one-to-one mappings. So pretty much all we're including in the codebook table is the class that's associated with the code, the actual code, the label, the column links to the column in the dictionary mapping table. And then finally, you can actually do resource links. So OWL same as links. So you can actually include a resource URI in the codebook. And then instead of doing a type link, it'll just link the column as same as the resource. Okay, so the timeline table allows you to do time intervals or time instances. So pretty much we include the end time, the start time. You can also include an in relation to here, the name of the timeline entry, the class that it maps to, and if there's a unit associated with it. So as you can see in the diagram here, this is kind of how the mapping happens. And yeah, for the most part, it's one-to-one mapping. The only thing is for start, end, and unit, notice that an instance is being created before linking the timeline column to the start time or end time. So the name is linked to the instance, which has the value of whatever start time, end time you provided. Okay. So finally, we have the property specification. I actually messed up the color on that. It's supposed to be dark yellow. So these are the default properties that we use. Actually, all right, that's better. Okay, so these are the default properties we use. As we mentioned before, it's mostly based on SIO. We are using prov for derivation and generation. And then we have a few annotation properties from RDFS and SCOS. Right, so pretty much the main thing here is you can replace any one of these properties or all of them if you want. However, if you do so, exercise caution. Make sure that the resulting thing is semantically consistent after you replace stuff. And the easiest way to do that is most of these things are object properties, except for has value, right? Or RDFS comment. So everything except for the annotation properties and has value are object properties. So if you're going to replace one of these object properties, don't replace them with a data type property, for example, or vice versa. So if you want to customize it, just use object properties where we have object properties and data type properties where we have data type properties. Okay, so now we can get into some examples. So I introduced the kind of specifications associated with the Semantic Data Dictionary, and now these examples should help solidify what this actually looks like. So as I mentioned before, the info sheet can contain data about the data set itself, as well as links to the other tables. So this info sheet example is assuming a set of CSV files. So relative URLs are provided, or absolute URLs, to the codebook, dictionary mapping, properties file, and so on and so forth. And it also includes metadata about the data set itself. So the examples I'll show here are from the NHANES dataset, which is the National Health and Nutrition Examination Survey. Okay, so I mentioned before this idea of object elicitation, or creating annotations for implicit entries. So those live in the dictionary mapping. So on the top left here, these are explicit columns within the demographic table of NHANES. So we're annotating these columns mostly with attributes, but here we see if you go to the ref person's country of birth, this is an example of column entry being annotated as an entity. And then you can also see that we're using a custom relation is location of to tie that birth location to the patient. Yeah, and for everything else that's annotated as an attribute, you see the attribute of is filled out here. There's also a label included. And for the unit, you see year and month, and that's actually an example of the code mappings at work. So over there is actually the class for the year and the class for the month, but that gets parsed based on the code mapping encoding. So what you're seeing here with the double question mark are what we refer to as implicit entries. And in the same way that you can annotate these dictionary mapping entries, the explicit entries, you can also annotate implicit entries. And in fact, you do it in the same table. But we're showing it as two separate tables because typically the columns you're annotating might not be the same. So in general, this isn't always the case because you can have an attribute of an attribute of an attribute of an attribute and so on. But in general, the implicit entries refer to entities. So for example, this sequen is the identifier of a participant, which we're including as NCIT subject as well as a SCIO human, and we're giving it the role of being a subject role. And we're doing this with all the implicit concepts included in the dictionary, the explicit entries of the dictionary mapping. Okay, so as I mentioned before, you also might have coded values in a data set. So this is what a codebook might look like. So for example, we see RIA gender, and over here, there's also RIA gender column. So this gender column is actually an encoded variable, which might be 1 or 2. So 1 for male, 2 for female. So now if we see those values, instead of just tagging that column as being of type biological sex, we also can tag the instances. We can tag it based on whether we see the value of 1 or 2 as also being of type male, and so on and so forth. So pretty much if you have coded values in your data, then you can use something like this to actually assign classes to those values. All right, so yeah, that's it for the examples. Actually, this is from Mimic. So actually, this representation example is based on a data dictionary for the Mimic admissions table. So a subset of the data dictionary looks something like that. It gets transformed into RDF through the process. And this RDF is just a graphical representation. So if I click this link here, so you see stuff like, so for example, this value up here, white ethnicity. So the class was, if we look back here, ethnicity is of type SCIO ethnicity. So in the demo, we're seeing it is tagged with ethnicity, but it's also tagged with this white based on the value. So pretty much this creates a graphical representation. We're seeing the properties being used, so is attribute of in relation to, and it all kind of links back to this subject. So it creates this like concise RDF representation from the tabular data based on the annotations you provide. All right, so so in order to evaluate this work, we evaluated it against the prior art. So these were the related work we mentioned before. So this relates to traditional data dictionaries, mapping languages, and data integration tools. So I'm actually going to refer the audience to the paper to actually look at this evaluation in depth. but I'll just present the results. So pretty much, we had several categories, those being data, semantics, fair, and generality. And we found metrics for each category. And we assigned a value of 1, 0, or 0.5 if the approach met the metric, didn't meet the metric, or partially met the metric. So actually, there was a lot of inclusion-exclusion work done in terms of what metrics we should include. We actually had even more metrics than these, but a lot of the metrics we had were not measurable, which makes it hard to include in an evaluation. So these were the metrics that we found which were the most measurable, and they're described in detail in the paper, so please read the paper. But in general, the STD approach performed the best out of these. So actually, the only thing that didn't perform great in the data category are traditional data dictionaries, but mapping languages and data integration tools, as well as STDs, met all the metric requirements. In terms of semantics, you'd think mapping languages would do better, but they only scored an average of half on all of them, where data integration tools did even better than mapping languages. And SCD did the best, getting a score of almost 90%. Traditional data dictionaries, as you could imagine, did really poorly in this category. In terms of fair principles, data integration approaches are mostly fair, whereas both STD and mapping approaches are met all the fair standards we were testing, which were pretty much the 4 main fair things: findable, accessible, interoperable, reusable. But we're also testing transparency and reusability. So mapping languages did as well as STDs. However, mapping languages are harder to use, arguably. And for generality, we also were tied with mapping languages and data integration tools. So in general, traditional data dictionaries performed poorly. The other tools did pretty well, but data integration did better than mapping and semantics, and mapping did better than data integration in terms of fair. But yeah, refer to the paper to see the in-depth evaluation. All right, so we're reaching the conclusion. So thank you, everyone who made it this far. So as with any ongoing project or ongoing work, there are limitations to our approaches. So one of the studies that we did as part of this research paper was we had an epidemiologist in our group, Jeanette, who presented these ideas, gave a brief tutorial to other epidemiologists and presented them with some documentation and had them annotate their own data sets. So from that, though, we found that even domain scientists were having a hard time with certain things. So one of the things we were saying, we didn't include this as a claim for this reason, but what we were trying to convey was that this approach will be usable to domain scientists more so than other approaches. So measuring something like understandability is a little difficult, but even though we're saying that our approach would be more usable, we did find that domain scientists did have some difficulties. So that's not to say they wouldn't have more difficulties with, say, a mapping language approach. But so some of these difficulties include they had a hard time representing complex ideas. So for simple mapping things like age or weight, they were able to do that. But for something else like the birth weight at the 3rd trimester, something involving time and a more concatenated concept, they had harder times annotating that. This idea of implicit concepts was kind of new to them. So getting used to that was a slight learning curve. And as I mentioned, like with this birth weight at the 3rd trimester or pregnancy weight, the mother's weight, whatever. These time association things took them a little getting used to. So these epidemiologists we were having do this study were not ontologists, right? And we pointed them to resources like OntoB or BioPortal or Perl or whatever to look for ontology terms. But even then, it wasn't always clear which term they should use. So my recommendation for this is whatever domain ontology or whatever general ontology you're using. So by default, you're using SCIO, or you can change it to use BFO or whatever. If you find a term in that ontology, that should be your preferred term. But in general, these general ontologies won't contain domain-specific terms. So then maybe have a preferred domain ontology that you want to use, and then try to find the term in that ontology. And if it's not there, have a secondary ontology and so on and so forth. Sometimes you might not find a term at all. And that kind of signifies, okay, maybe you need to create your own ontology. Maybe this domain hasn't been covered to the degree that you need in order to describe the data in the domain. Okay, so due to this challenge, another limitation is that the user should have at least minimal domain knowledge so they know what the data means, and minimal ontology knowledge so they know how to find a class in an ontology, and so on and so forth. Another limitation of this approach is that it only supports the annotation of tabular data. So while something like Settler can be used on XML, at this point, we can't use semantic data dictionaries on XML or on unstructured natural text. The annotation process itself is mostly manual. There has been some work in automating it, and it's an open research problem that we'd be happy to have students work on. But it is pretty challenging, and it involves a lot of natural language processing, and even then trying to come up with the best match is difficult. I think Matt Johnson is here, and Shruti's done some work on this as well. So maybe Matt can talk about the automatic annotation process at some point, if you guys ping him or something. But the process so far, especially what we've been doing and what we discussed in the paper, is mostly manual. So that is a limitation. And like all our work, we can improve in terms of documentation and tutorials. That's what we're notoriously bad at TWC since Tim Lebo left. But we do have documentation available. So some closing remarks. We addressed the limitations of prior work, in particular of traditional data dictionaries, and therefore this work helps advance the state of the art. And the SDD approach is fair in that the results generated are findable, accessible, interoperable, and reusable. So there are some resources. So SDD to RDF is a tool for converting your SDDs into knowledge graphs. There's some documentation available online. There's also example SDDs and actual research projects. So for example, I mentioned NHANES and Mimic. The actual SDDs we created for those are publicly available. And this also links to the journal paper. So this was a collaborative effort between several institutions, and here are the authors that were included who contributed to the journal paper. And I think that's it. Some references there.
All right. Thank you, Sabbir. We've used up our hour, but I did have one question regarding, do you have tutorials as part of the documentation?
Right. Yeah, so as part of this documentation link, actually let me click it. There is a tutorial component which shows you how to set up a Vagrant VirtualBox. I don't know why, But then, yeah, it tells you clone the repo. It tells you how to get set up with STD to RDF. Gives you an example configuration file, stuff like that. And as part of the resources, actually, let me actually go back. Yeah, so there is a tutorial that goes through an example that people can go through. And as well as it shows you how to create a swirl rule for doing inference over ontology-generated content, as well as how to query it. But if you actually go to the resources, we have resources for all these datasets: Civic, FAIR, Mimic, NHANES, Seer, Cynthia, GDC. And we have this template project. So what people can do is they can create a copy of this template project and just update the contents, and then they already have a starting project that they can start generating knowledge graphs from. Okay,
that answers my question. Okay, so let's thank Sabbir for this very comprehensive presentation. I was proxy for everybody clapping, Sabbir.
Good job.
Yeah.
Thanks.
And I'm going to stop the recording now. All right.